Okay, I made this video to help you basically with acid-base calculations. And a couple things to think about. You have a bunch of equations that are always going to be available to you when you're doing any sort of acid-base calculations. You're always going to have the pH is equal to the negative log of the hydronium ion concentration. And the POH, remember P just means negative log, that's what it means. Negative log of a hydroxide ion concentration. Would that be saying, that the pKa is equal to the negative log of the Ka? We don't need a bracket there. It's not a concentration. Negative log of the Ka. And of course the Kw is equal to 1 times 10 to the minus 14. This is the equilibrium constant, so that is constant. It changes with temperature. And we know that is equal to H3O positive times OH minus. And as a result of taking a negative log of this thing, we can wind up with the negative log of Kw, which is 10 to the minus 14, is equal to the negative log of the H3O positive concentration times the OH minus concentration, which ultimately gives us 14 is equal to pH plus POH. Okay, so the negative log of 10 to the minus 14 is 14. You should know that the log of 10 to the third is equal to 3, because that's a log base 10. Remember, your appendix does review stuff like this. That's kind of like asking 10 to the what equals 10 to the third. Okay, so it obviously is 3. So that means if you have the negative log of 10 to the minus 14, it's going to equal 14. Because these equations are always going to be available for you for solving these problems. It's important to realize that. Now, what do we mean when we're comparing, say, for instance, something like a strong acid or strong base? Anything I say about acid, you can apply to base. So, which means if I have a strong acid, that means it goes completely to this. So, if I start out with a 10 to the minus 3 molar solution of HCl, I will wind up with 10 to the minus 3 molar of H3O positive, which ultimately means the pH is simply going to equal the negative log of your initial concentration. And you will have a pH of 3 solution there. Okay, that's the key to a strong acid, strong base. You don't need to do a Rice table. It is just the negative log of the concentration. Now, if my concentration had been 3.5 times 10 to the minus 2, well, most people can't do those logs in their heads, so you have to put that in your calculator. And you would just do negative log of 3.5 times 10 to the minus 2. Remember, try to use 3.5 second EE negative 2. It's less likely to make mistakes, and it is actually faster, less keys to press. So, I think I gave you a problem in your slides that was comparing like the pH of, I believe, I can't remember if it was a base or an acid. I think it was actually a base, where we compared the pH of like a weak base to a strong base. And for the weak base, the strong base is just the initial concentration. The weak base, well, remember what we did. We have this shorthand notation now. So let's say you have a weak acid. And I really shouldn't write it like that because it's an equilibrium and it's not going to favor the right side much. So we get, and I'm just going to write it without the water, H positive plus A negative. It's just a standard way we write weak acids. Okay, let's just say the Ka is equal to 10 to the minus 11. Okay, well, let's actually just put it in a normal form. Let's say it's Ka is equal to 2.8 times 10 to the minus 11. Okay, now your initial concentration, whatever it is, let's just say it's 10 to the minus 3. This would be 0. This would be 0. This would be minus x, x, and x, plus x, plus x. 10 to the minus 3 minus x, x, and x. You wind up with x is equal to, now remember the shorthand notation, because the equilibrium expression, this winds up being x squared over 10 to the minus 3 minus x, right? Because it's a weak acid, and the way your book defined you can use this estimate is we can say that that x is small. Remember, if you look at your slides from, I guess that's chapter 15, we could say this is small, and we had said you can do that as long as your initial concentration of your acid, and I'll write it like this, is greater than 500 times the Ka. And I think I said in my video, I'm okay with 100 times the Ka for a class like this and for multiple choice questions. It's going to suffice you fine. So that's all we mean, is that 10 to the minus 3 is much greater than 2.8 times 10 to the minus 11. You're talking about what? 8 orders of magnitude. I'm suggesting only 2 orders of magnitude, and you're only going to get a 5% error. So we can eliminate that x, which means whether this be an acid or a base, your x is always going to equal, once you learn this shorthand notation, the square root, as you solve this, right? Because this is all equal to your Ka, okay? This is the initial concentration right here, okay? So it becomes the initial concentration times the Ka. That's all x is equal to. And x is equal to, in this case, H positive. See where we're going with this? So this is your shorthand notation. You don't have to set up the Rice table. You simply look at your Ka. You simply look at your initial concentration. If this holds true right here, then you simply do x is equal to the square root of the initial concentration times the Ka. And since the pH, if the question is asking you for a pH, is just a negative log of hydrogen ion concentration, it ultimately becomes the negative log of the square root of HA naught times Ka, and this is a concentration. And then you have your answer. And the only thing we do is we change, if this is a base, we'll just realize that X is now equal to OH minus, not H positive. So if you're asked for the pH, there's one additional step, because when you solve for this, X will be OH minus. You're then going to need to use your expression like this. Whoops, why isn't that writing? Expression like this, or just something like this. You get your POH. Take the negative log of the OH. Either way, you're going to have to do that additional step. But that's really the difference between strong and weak. Strong is just the initial concentration. Weak is going to be the initial square root of the initial concentration times the Ka, and if it's a base. So that's one of the important things I wanted to delineate for you here and really stress when you look at these problems. So when you get a problem on an exam or smart work, whatever, immediately look at whether or not you can use the shorthand. Now, I will tell you, your book wants you to use this as your estimate. So if it's not that, you might get the wrong answer for the back of the book or the smart work. I don't think there's too many questions that you'll see a difference between that in terms of smart work in the back of the book. I haven't looked at each one individually. Just need you to be aware of that. That it might be that it's not falling under this criteria here, but is falling under this criteria here, and you're going to get the wrong answer. What else? Acids and bases. The last thing then I really want to talk about then is just the salts, because this can be confusing. So if, and we talked about this, if you have a salt, something like, let's just use this for example, sodium carbonate. When this dissolves in solution, obviously, you get the 2 sodium ions plus the carbonate ion. Since the carbonate ion is we won't call it a strong base, but relatively speaking, it's stronger than water, if you will. So it will react as a base, and that's because this is a weak acid, carbonic acid, right? And this then ultimately is even a weaker acid. And it's also a base. What's unique about this, it can act as an acid by picking up a hydrogen ion and forming this, or it can act as a base and forming this. From this being weak initially, this being even weaker, this makes this a relatively strong base. And I don't want to say strong base. It's not a strong base, but I want to talk relative, which means in solution, ultimately, this will happen. You get HO3 minus plus OH minus. So this is a salt that is actually acting as a base in solution. And that's one of the keys here. So you need to spend a little bit of time on this, on acidity of salts. And it's an important topic. So that's really all I wanted to say on this video.